Hi, Gibson here. So today we're going to look at the last topic in this unit that we've been working on that includes momentum and impulse and work and power and energy. And the topic today is about the principle of conservation of energy. So let's look at our objectives. First, we'll be able to state the law of conservation of energy. And then we're going to work on some problems and go through an example where we can demonstrate or understand how total mechanical energy is conserved. All right, so what does the law of conservation of energy say? It says energy cannot be created or destroyed. It can be transformed from one form into another, but the total amount of energy never changes. So this really has profound implications for the world we live in, for the universe that we live in that there is a finite amount of energy available or in existence, and we can't create more. We're not going to destroy it, but it can be changed from one form to the other. So what are some of those different types of forms of energy? Well, we've already talked about potential energy, right? Energy due to gravitational position when we lift something up off the ground. Another example would be winding up a spring, right, that could create another form of potential energy or spring energy. We've talked about kinetic energy, energy of motion. Heat is a form of energy. Sound is actually a form of energy, right? It takes energy to produce sound. Chemical energy, electrical energy, we can have energy in magnetic fields. So there's a whole variety of different forms that energy can take. And most processes and actions that occur in the world are include, right, having energy shift from one of these forms to another. Think about what we do as humans, right? We take chemical energy, the food that we put into our body, and we convert that into kinetic energy, right? That helps us move around. We convert it into heat energy that allows us to maintain our body temperature. We convert it into sound energy as we talk and make noise. All right, let's look at a specific application of this concept where we apply it to what we're going to call total mechanical energy, TME. So total mechanical energy is looking at just two of those types that we listed on the sheet a minute ago, kinetic energy and potential energy due to gravity, okay? So the classic example of this is a pendulum. So a pendulum is simply a mass hanging on the end of a string that swings back and forth, okay? And it's a great example because a pendulum is constantly transforming from kinetic energy to potential energy. So let's see how that works, right? When it's at the maximum height, the pendulum or the mass is going to have all of its energy and potential energy. And we can calculate that by mass times gravity times height, right? The acceleration due to gravity. That's what we worked with in the previous lesson. Now, as we release the pendulum and it begins to swing, right, it's going to lose potential energy. And as it speeds up, it's going to gain kinetic energy. Right? So we'll just watch this animation here. You'll see it reaches its maximum kinetic energy when it's right at the bottom. That's where it's going to be swinging with the greatest velocity. And then at that point, right, it has zero potential energy. We're going to call that zero because that's the lowest point or height of the pendulum. And then as it swings back to the top on either side, right, all the energy is restored into potential energy. Now, in a perfect pendulum that had no resistance or friction, air resistance perhaps as it travels through the air, it would continue to swing back and forth forever. But we know that's not the case in the real world, right? We begin to lose mechanical energy into the form of typically heat, right? As it travels and produces frictional forces through the air resistance, or perhaps some frictional force where the string or cable, right, is swinging back and forth depending on how it's attached. Here's another example of conservation of energy, like a roller coaster, right? This is classic. So how do roller coasters actually work, right? They have a drive system that initially takes you in your car up to the top or highest point of the roller coaster. But from then on, it's gravity causing you to accelerate downward, and you're constantly converting back and forth between kinetic energy as you speed up and potential energy as you head back up to the high point on a track or go through a loop, as we see here in this example. Okay, so just take a minute and observe. Notice our graphs over here on the right. It shows kinetic energy in red, potential energy in blue, and total mechanical energy in green. Now, this is a perfect roller coaster in that we're not losing any energy to friction or air resistance, because if you notice, the total mechanical energy remains the same here. But we do see it shifting back and forth, right? When we start at the top, all of the potential energy, or all the energy, is in the form of potential energy. When we finish at the bottom, right, all of the energy is in the form of kinetic energy. That's where we reach the maximum speed down at the bottom. Looks like around 37 meters per second. Okay. All right, so two examples, a swinging pendulum and a roller coaster. If we ignore friction or air resistance, then total mechanical energy is conserved, and we just simply shift back and forth between kinetic and potential energy. Now, let's apply a little more math here. Let's quantify this relationship that exists in the law of conservation of energy. And notice it's similar to what we did for conservation of momentum, right? Where we have the energy before, the initial energy, is equal to the energy after. But we've added another term into this. Notice we have a W external, that is work external. So if there is external work being done, then we will not have conservation of total mechanical energy, okay? The work is going to change the overall energy level of the system one way or another. So this equation that I'm giving you here quantifies this relationship between work and the two forms of mechanical energy, kinetic and potential. So how do we know whether work is external? Okay, if there is external work being done on the system, it's typically done by these types of forces. So if we pull or push, right, tension or applied force to the system or the objects in the system, we're applying an external force or external work. Friction, we talked about, normal force, air resistance force. These are all examples of external work being done to the system. So if these forces are present, then the total mechanical energy before is going to be different than the total mechanical energy after, okay, or final. Now, what type of work is done by forces that are considered to be internal? So here's forces that would be considered internal: gravitational force, spring force, electrical force, magnetic forces. Okay, these are forces that are part of the overall system and therefore do not get considered as external work. Okay, so if these are the only forces present, then total mechanical energy is going to be conserved. There'll be no change between the energy initially and the energy in its final state. So that's what this statement here says. If there is no external work done on the system, total mechanical energy is conserved. Now, a couple more things with regard to this formula. If the external work that we're doing is positive, then it's going to increase the total mechanical energy. You can see that in the equation, right? If that's a positive number, then we're going to have a greater final energy than what we had initially. On the other hand, if the work done is negative, then it's going to decrease the total mechanical energy. So sometimes we have to look at the force and ask ourselves, is this going to increase, right, either kinetic energy or potential? In that case, we'll treat it as positive, or is it going to decrease kinetic energy or potential energy? If so, that work is going to be treated as negative. So typically friction and air resistance forces, right, are going to always be considered negative work and decrease the mechanical energy. A push or pull force, well, it depends what direction we're pushing or pulling, right? If it speeds up the object, then that would be considered positive work. If it slows down the object, then that would be considered negative work. Okay? All right. So let's look at an example here in a little more detail. We have a skier going down a ski slope. And our assumptions are going to be that as he travels down the slope, initially the friction is very low or negligible. You can ignore that. But then he hits the bottom of the hill and he hits the rough, unpacked snow. And as he hits that rough, unpacked snow, he's going to slow down. So he begins to encounter friction in that bottom stretch of snow. Now, what else are they showing us here on this graph? Notice we have our energy bar graphs again. And take a look at, as this replays, that all of his energy is potential when he starts at the top of the hill, right there. Okay, notice we have all potential energy, but as soon as he begins to slide down the hill, kinetic energy increases, potential energy decreases. But up until that point, right, the total mechanical energy, the green bar, is constant. But now look what happens as he hits that snow and the frictional force begins to act on him. Watch the bar graph here. We'll see that the work bar starts to grow in the negative direction. Okay, so right there, we begin to see negative work being done on the skier. And what happens? Well, that slows him down, so his kinetic energy goes to zero, but also the total mechanical energy becomes zero. So in this example, the total initial energy that he had, either at the top of the hill in potential energy or at the bottom of the hill with kinetic energy, all of that energy winds up as negative work, or basically that frictional force is going to change it into the form of heat. Okay, so here again we have maximum potential energy at the top, maximum kinetic energy right at the bottom, and then the frictional force is going to do the negative work to reduce the kinetic energy to zero. Okay, so there's an example where in this case total mechanical energy is not conserved, right? The frictional force converts that energy into, in this case, heat, and probably even melts the snow a little more. All right, so let's take this problem and actually apply a little bit of math here to it, see if we can analyze this, okay? So here's what we're going to find. One, what is the maximum potential energy of the skier? What is the maximum kinetic energy? And how much work is done by the friction of the snow, the frictional force? Now, a couple key assumptions here. We're going to use 9.8 meters per second as our acceleration due to gravity. The numbers just come out a little closer to each other. And let's assume that the skier has a mass of 40 kilograms. Okay, so that's what we know, the mass of 40 kilograms. But two other really important values are, what is his maximum height? Because that's going to let us calculate the potential energy. So if you watch the animation, when he first starts right at the top of the hill, you'll see that he has a maximum height of 52 meters. And then his maximum velocity when he hits the bottom of the hill before the friction is 31.9 meters per second. Okay, so remember those values. We're going to use those here as we calculate potential and kinetic energy. All right, so let's calculate each of these. First, maximum potential energy. So we know the equation for that is mass times the acceleration due to gravity times the height. Okay, so let's plug in our numbers here. We have 40 kilograms for our mass. We're going to use 9.8 in this case for acceleration due to gravity. And we know the top of the hill was 52 meters high. So we multiply all those together and we get about 20,000, a little more than 20,000 joules worth of potential energy. Now let's calculate his maximum kinetic energy. So 1/2 mv squared is the formula we use for that. Right, so let's put in, again, 40 kilograms for the mass, and the 31.9 meters per second squared. That was the maximum speed of the skier right at the bottom of the hill. And that gives us, you can see, actually very close, right? About 20,352 joules. So these are very close to each other, probably just a rounding error in terms of the values that we picked, but we can see that for the most part, all of the potential energy at the top of the hill, right, was converted into kinetic energy at the bottom of the hill. Now, how do we calculate the work done by friction? So we go to our equation for conservation of mechanical energy, and we want to solve for the external work. Right? It's being done in this case by the friction of the snow against the skis. So let's plug in values here. We know that initially at the top of the hill, all the energy was potential. So we put in 20,384 joules for that. The kinetic energy at the top of the hill under the initial conditions was 0, right? He was at rest. He had not started sliding down the hill yet. Plus the work equals, and then at the final conditions, right? He's at the bottom of the hill, so potential energy is 0, and he comes to rest. So the kinetic energy is 0. All right, so we have an equation that's quite simple here because all these 0 terms are just going to drop out. And to solve for the external work, we just need to subtract, right, the initial potential energy. So we get about negative 20,384 joules worth of work done by the friction of the snow. And notice, we kind of knew it would be negative work, right, because it decreased the total mechanical energy, but the math should also confirm that and give us a negative value here. Okay, so that's it for this lesson, right? We know how to state the law of conservation of energy, and we are able to solve problems for total mechanical energy when it's conserved or when there is external work being done to the system. All right, so that's it for the lesson here today. Check out the assignment that goes along with this in Google Classroom.